yesterday we moved into two slightly different topics. Remember, we started this module with a conversation on different reactions: decomposition, formation, and combustion reactions. And in the combustion reactions, we had the combustion of metals, which we said could be something explosive, could also be rusting. Those are both combustion of metals, because combustion is primarily a reaction that involves oxygen. So when something reacts with oxygen, it's combustion. It may not look like a fire, it may be, like I said, rust, but that's still considered combustion. And other than the combustion of metals, we had two other types of combustion that we differentiate within that general category of combustion when we're burning fuels, generally a carbon-hydrogen chain, and that is complete and incomplete combustion. Now the products of combustion, if it's not the combustion of a metal like in rusting, but generally speaking, if we have a fuel that's burning or a fuel that's combusting with oxygen, the products of that combustion are going to be carbon dioxide and water. And you will not be given that. You'll be expected to know that the products of combustion are typically carbon dioxide and water. So if the question says propane is combusted, or propane goes through a combustion reaction, well then you would know propane and oxygen produces carbon dioxide and water, because those are the molecules involved. That's why I sometimes refer to the CHO molecules, the carbons, the hydrogens, and the oxygens form CO2 and H2O, CHO molecules. So then we had complete combustion, we had incomplete combustion as well. Remember that incomplete combustion means that there's insufficient oxygen in the space to support the creation of carbon dioxide. And since basically the system is running out of oxygen, there's limited oxygen, the combustion then reverts to a secondary, another molecule which is not preferred but is possible, and that's carbon monoxide, CO. So rather than CO2, we're producing CO. That CO is poisonous. CO2 in general amounts, stuff we're used to, is not poisonous. And so it's important for us to have combustions, especially those that are inside of our homes, inside closed spaces where we tend to be, that they are working efficiently, that they're getting plenty of oxygen for combustion, so that they're producing carbon dioxide, not carbon monoxide. Because, for example, if you use one of those outdoor heaters, they say don't use indoor, but you use it indoor anyway, it very well may start producing carbon monoxide, and you will poison and kill your whole family. Okay. Unless that's your plan, in which case we'll talk. Okay. Most typically you hear about the catalytic converter in cars. That's a typical example where the engine produces both carbon dioxide and carbon monoxide at different times, and the catalytic converter converts the carbon monoxide into carbon dioxide. Or you might have noticed, maybe you haven't, but a lot of times when they have internal combustion, like for example a water heater that might be running on gas, or a fireplace that actually uses gas inside the home, that they will run the combustion air into the combustion chamber from the outside. What they'll do is they'll bring the air that's needed to support the flame. They'll bring it from a source outside of the room. That way the flame itself is not burning oxygen that's in the space where you're living. So that if anything happens, it's not using up the oxygen that you need to breathe. It's using up oxygen that's coming in from outside. Because the flame that's under that hot water heater, it doesn't care if the air, the oxygen that it's using is at 30 degrees Celsius or -5 degrees Celsius. It doesn't care. It's just oxygen. We care. We take the effect of that combustion in a separate system. We capture it and it heats our water or heats our space, things like that. So you have a separate combustion air from the room air to make sure that the flame, the combustion process, does not consume the oxygen that you need to breathe. Okay. That was actually 2 days ago. So if you weren't here yesterday, some of that should have been familiar to you. But yesterday we started to also talk about the concepts of mass, molecular mass and atomic mass. And yesterday we put on the board a statement of equality, an equation, which means we can create conversion factors from it. Remember, just put one on the numerator, one on the denominator. Since they're equal, the product of division, or the result of division then would be a 1, so it doesn't really change anything. It just translates it kind of into another language. We wrote down that 1 AMU equal to 1.66 times 10 to the negative 24th. 1.66 times 10 to the negative 24th grams. And so we have a way now of converting between units. We get to translate between the languages of AMU and grams. And we're used to grams, but what's an AMU? We said it was an atomic mass unit. And an atomic mass unit is a unit of mass that's used to describe, or excuse me, to indicate the mass of extremely small particles. In other words, we're taking the mass, I almost said weight there, right? That's not technically right. We're measuring the mass of individual atoms. Part of something I may not have mentioned yesterday, but how did we come up with this idea of an AMU? Well, what they did was they took carbon-12. Carbon has an atomic number of 6, an atomic mass of 12, meaning that there's 6 protons, 6 neutrons, and 6 electrons, right? And they took the mass of a carbon-12 atom and they divided it by 12. And so one AMU, you can think about it, is the mass of a proton or a neutron and the electron. Remember I said yesterday the electrons really are so small that you can kind of think of them as not matter. They don't really matter because I related it to a bowling ball. Let's say a proton is a bowling ball and the electron is like a piece of sand. If you're taking the mass of the bowling ball, you're not going to run up and say, wait a minute, I need to make it exact and drop a piece of sand on it. In scale, it's so big, it's virtually nothing. So we often think about it as just simply the mass of a proton or a mass of a neutron. That's not technically what it is. It's 1/12 the mass of a carbon-12 atom, which means it takes into account protons, neutrons, and electrons. It takes all that into account. But whenever we look at the periodic table and we find the mass of an individual element, the atomic mass, for example, sodium here is approximately 23. That tells me two things, right? It tells me, first of all, that the mass of one sodium atom is 23 AMUs. Before we didn't know what, we said, what is mass? The mass is the number of protons plus the number of neutrons. That's a count, right? That's not really a mass unit. That's a count number. We said it's atomic mass. What is that? What is it really? Well, the mass is 23 AMU. 23 AMU represents a certain number of protons, electrons, and neutrons. Okay. While sodium may be 23 AMU per atom, we also know from the periodic table that sodium is also 23 what? You read it over here. Sodium, it's 23.0 AMU per atom, right? 23.0 AMU per atom. There's 23.0 AMUs, which is a mass unit, for every atom of sodium. But that number also tells me something else. It tells me that sodium also has a mass of 23.0 what? Do you remember from yesterday? It's 23.0 AMUs per atom. It's also 23.0. It's 23.0. It's a mass unit, right? So what would be a mass unit? Grams per mole. Yeah. Just trying to keep that mole thing coming and tease it out, okay? So when I look at the periodic table, I can determine the mass of an individual atom, but that same number with the different units gives me other information. It's 23.0 AMUs per atom. It is also 23.0 grams for 1 mole. And we mentioned yesterday that 1 mole is 6.02 times 10 to the 23rd of them. It's a huge number. Huge number. But it's still just a unit of counting. And we related it to a couple, a pair, a dozen, a score, all these different units which mean something. A dozen means 12, a baker's dozen means 13, a score means 20. A mole means 6.02 times 10 to the 23rd of them. So if I said, give me 1 mole of something, your response would be, here's 6.02 times 10 to the 23rd of them. I need a mole of, and hopefully it's something really, really small, right? Because, and forgive me if this is wrong, but I want to give you some sense of scale, and I'll try to find a video that talks about this. Something to the effect of, if we had 6.02 times 10 to the 23rd ping pong balls, it would cover the Earth a depth of a mile. Okay, we're talking about a huge number of something here. This is a massive number of them. But why do we need such a massive number? What? Because you're not capable of giving me just one of them. I can't come to you and say, give me 1 sodium atom. It's too small. We don't work in that small of a scale. So I need to ask for a lot of them. If I ask you for a couple of them, it's too small. If I ask you for a dozen of them, it's too small. If I ask you for a score of them, it's too small. If I ask you for 1,000,000 of them, it's too small. Give me 6.02 times 10 to the 23rd of them. Now it's something you can actually see and hold in your hand. I mean, think about that. Such little mass in your hand, and if we were to take the size of that and blow every one of those atoms up to the size of a ping pong ball, we would all be a mile deep in ping pong balls around the whole world. That's the scale of what we're talking about. It's massive. It's an incredible number. When I say it's massive, it's not really. It's very small in terms of mass, but it's huge in terms of the count. Now, one thing I alluded to, but I didn't go really deeply into, was the idea of this is the atomic mass, right? How do I come up with the molecular mass? Let's say, for example, sodium, that's fine, but I want to know what is the molecular mass of sodium chloride, NaCl. Well, we mentioned about a decomposition reaction. If I've got sodium chloride, it's going to produce sodium and chlorine, right? So whatever mass I started with has to be equal to the mass I end with, the conservation of mass. So if I want to figure out the mass of this molecule, what I need to do is add up the mass of the individual parts. The mass of the molecule is equal to the mass of the sum of the parts of the molecule. So for sodium chloride, I've already figured out the mass of sodium chloride. Sodium chloride is 23.0. I'm just going to write that number there because I know it's got 2 different units I can go with, right? So 23.0, what's the mass of chlorine? Come over to chlorine, column 7. 35.5, let's round it to 35.5. So if sodium has a mass of 23.0 AMU, let's go ahead and stick with AMU. If it's 23.0 AMU and chlorine has a mass of 35.5 AMU, the mass of one sodium chloride molecule must have a mass of 58.5. We just add them together. 58.5 AMU. Make sense? Now here's the other part of it. Okay, how much does 1 mole of sodium chloride? What's the mass of 1 mole of sodium chloride? Well, the mass of 1 mole of sodium is 23.0 grams. And the mass of 1 mole of chlorine is 35.5 grams. So the mass of 1 mole of sodium chloride must equal 58.5 grams. Now, I hadn't planned this, but I think I've got salt over here, so let's go ahead and do a quick impromptu mini lab. See if we can do it. Don't see my salt. Don't get to see my salt. Well, I'll go ahead and bring in some so we can actually see this. But if I were to go, basically the point here being is if I wanted to have 1 mole of salt, and why I would ever want 1 mole of salt will make more sense in just a minute, okay? But if I wanted to get 1 mole of salt, what I would do would be over here, take my triple beam balance, make sure that it's centered, then go ahead and set it to 58.5 grams, and just slowly add salt until it goes back to level. And the triple beam balance would say, okay, stop. You now have 58.5 grams of sodium chloride. And when I get to 58.5 grams of sodium chloride, how many sodium chloride molecules do I have? Well, 58.5 grams is the same as 1 mole of sodium chloride. And because it's 1 mole of sodium chloride, that means I have 6.02 times 10 to the 23rd molecules of sodium chloride. Okay? So by knowing the mass of 1 mole of something, I can figure out how many individual atoms or molecules of that thing I have. Why would that be important? Well, let's go ahead and I'm going to keep the components here the same. I'm going to reverse this arrow and make it a formation reaction, pointing back towards the molecule. So I've got sodium and chlorine that are combining to make sodium chloride. If I wanted to make 1 molecule of sodium chloride, how many atoms of sodium would I need? 1. How many atoms of chlorine would I need? So 1 and 1 makes 1. If I wanted 10 molecules of sodium chloride, how many sodium atoms would I need? If I want to make 10, then I need 10 and 10. Because for every 1, I need 1 and 1, right? For every 2 I want to make, I need 2 of this and 2 of that. They combine together. For every 10, I need 10 and 10. For every 20, to make 20, I need 20 and 20. To make 50, I made 50 and 50. To make 100, I need 100 and 100. To make 200, I need 200 and 200. To make 500, I need 500 and 500. To make 1,000, I need 1,000 and 1,000. Things going? Are you starting to get the drift here? Is there a pattern you're seeing? Remember the coefficients? To make the implied 1, there's a 1 right here. We don't write it, right? In order to make 1, we need to have 1 and 1. They look like zeros, but I'm trying to emphasize the fact that it's missing. But 1, to make 1, we need 1 of each. And that's why you can have 1 piece and 1 piece combined to make 1 piece. Why? Because this is formed by adding those together. If I have 1 mole of this and 1 mole of this, they combine to form 1 mole of this. For every 2, I make 1. I have twice as many pieces on this side, but when they combine, they form 1 larger molecule rather than individual atoms. And so when I went through that process saying, to make 1, I need 1 and 1. To make 5, I need 5 and 5. To get us up to the place where it makes sense that in order to make 6.02 times 10 to the 23rd of them, I need 6.02 times 10 to the 23rd of these and 6.02 times 10 to the 23rd of that. And because they relate to AMUs, but they also relate us over to grams, I can say, if I want to get 6.02 times 10 to the 23rd atoms of chlorine, then I need to measure out 35.5 grams of chlorine. And if I want to have 6.02 times 10 to the 23rd atoms of sodium, I need to measure out 23.0 grams of sodium. And when I react those things together, it's going to make 6.02 times 10 to the 23rd molecules of sodium chloride. And that sodium chloride is going to have a mass of 58.5 grams. Why? Conservation of mass. This mass and this mass can't be destroyed. Nothing can be added. It needs to be the same. It's not a perfect analogy because we actually make something else, but think of it this way. If I have 5 cents and 5 cents, I can make a dime. If I have a nickel and a nickel, it's worth a dime, right? Now, it's not a perfect analogy. It actually has flaws for chemistry, but if you're having trouble with this, just think of it that way. I can take a nickel and another nickel. How many nickels do I have? 2 nickels. What do they make? What are they worth? 1 dime. So I'm making fewer things, but actually each thing is going to be more massive. I'm taking something that's 23 AMU and 35.5 AMU, but when I smash them together, I've got fewer things because they become something else. They become a third new thing, which is made up of the 2 original things, but the mass is the sum of the masses. That brings us up, I think, to 260. Actually, they use sodium chloride in there as an example near the middle of the page. So let's just take a moment. I'm going to write it on the board, but let's look at page 260. And it says that people are encouraged to limit their salt intake to 5 grams per day. How many moles of sodium chloride is that? So if you're only supposed to take in 5 grams a day, how many molecules of salt are we talking about? How many actual molecules make up 5 grams? Well, you see in there that they do the mass relationship of sodium chloride. The mass of sodium chloride, just like we did here, is the mass of 1 sodium and the mass of 1 chloride, which is up to be 58.5 AMU. So 58.5 grams of sodium chloride is equal to 1 mole of sodium chloride. Okay, that's a statement of equality there. So it becomes a conversion factor. So when we use that conversion factor, we have 5 grams. We multiply it by the conversion factor of 1 mole is equal to 58.5 grams. So 5 times that conversion factor gives us 0.0855 moles. Now that I have moles for the first step, now I can figure out how many actual molecules I have. Right? Because if I can get from grams to moles, then I can go from moles to pieces, individual pieces. And that's what the very last part of 260 shows you. And then the top of 261. I have 5 grams, which is the same as 0.0855 moles, and then each mole is 6.02 times 10 to the 23rd, which gives us another conversion factor. You see that on top of 261, where 0.0855 moles times the conversion factor of 6.02 times 10 to the 23rd molecules for every 1 mole of that molecule results in 5.15 times 10 to the 23rd molecules of sodium chloride. So 5 grams is the same as 5 grams of sodium chloride is equivalent to 5.15 times 10 to the 23rd molecules of sodium chloride. Now the doctor could say, hey, limit your salt intake to 5.15 times 10 to the 22nd molecules of sodium chloride a day. How are you going to even relate to that? I mean, because we're not used to working in individual counts per molecule, but we can relate in some way to 5 grams. Okay? But recognize when you're saying grams, you can convert it into moles if you know what the substance is. So you can go from a mass to a piece count, or from a piece count to the mass using the mole concept and the atomic mass or molecular mass concept. Let's move forward to 264 past the experiment and look at on your own 7.7. Question asks, how many moles of scandium are in a 50 gram sample of scandium?
was that again?
Page 264. So again, just what we need for the questions is on your own 7.7. Ask the question, how many moles of scandium are in a 50-gram sample of scandium? So, start attacking the problem. I have grams, I want to get to moles, right? Let's set up what we do know. We know that we've got 50 grams of scandium. We'll put that all over 1. It's our known. We're going to have some kind of conversion factor, right? We can assume that, to produce something in units of moles. Standard setup, we use this all the time. So we've got grams of scandium over 1 times some unit conversion factor that's going to produce an answer in the units of moles. So we've done this enough times to know that grams of scandium on the top needs to go to the bottom, and the units of moles needs to go on the top. Right? I don't know the numbers yet, but I know the units. So I need to figure out a unit conversion factor that relates moles of scandium to grams of scandium. They don't give me one. So I need to know where to look for it. Either I have to have it memorized or I need to know where to go find it. So how do I relate moles to grams for scandium? Right, come over to the periodic table. Find scandium, atomic number 21. We note that its mass on this chart is 44.9559. So we're going to assume it runs up to 45. Okay, I'm going to make that assumption. It's going to be 45. So if the atomic mass of scandium is 45 AMUs per atom, it's also 45.0 grams per 1 mole. The periodic table with the atomic mass of scandium gives me a number which, when I use the units grams per mole, is the mass of scandium as well. So for 50 grams of scandium times 1 mole per 45 grams of scandium is going to give me my answer for moles. So it's basically 50 divided by 45. So it's going to be greater than 1, because if it was 45 over 45, it'd be 1. We estimated here, so we're going to have 5 extra over 45, 1 over 9. So it's going to be 1.111, something like that. It's like a 1.1 repeating. Check the book real quick. .11 moles, okay. So it's 1.11. 1.11 moles of scandium. So when I have 50 grams of scandium, I have 1.11 moles of scandium. Now, how many atoms of scandium do I have when I have 50 grams? Well, now I just take my 1.11 moles of scandium, put it all over 1, and I need some kind of a unit conversion factor that takes me from moles to atoms to produce an answer in atoms. So 1.11 moles of scandium. Here, there's a unit conversion factor that applies to every single element out there, and every single molecule out there, and every single zebra out there, and every single goldfish out there, right? Because it doesn't depend upon what it is, it's just a unit of count, of counting. And we know that 6.02 times 10 to the 23rd of anything is the same as 1 mole of that anything. So 6.02 times 10 to the 23rd atoms of scandium is 1 mole of scandium. Moles cancels moles, and I'm left with atoms. And I do the math. So it's going to be 6.66 times 10 to the 23rd atoms of scandium for 50 grams of scandium. It's 1.11 times 6.2 times 10 to the 23rd. So somewhere around 6.66 times 10 to the 23rd atoms of scandium for every 50 grams of scandium. Now I know how many pieces I have to react with something else. If I'm making sodium chloride and I know how much sodium chloride I need to make, I know how many atoms of sodium I need to buy. And I know how many atoms of chlorine I need to buy to make a certain number of atoms of sodium chloride. But we don't work in atoms, we work in mass units bigger than that, so grams, let's say. If I need to make a certain number of grams of sodium chloride or kilograms of sodium chloride, big production, right? If I need to make, and we don't generally make it, we mine it, but anyway, if I were making it in a lab, I was making sodium chloride, and I wanted to make a certain amount by mass, then I can figure out exactly how much mass of sodium I need and how much mass of chlorine I need in order to produce a given mass of sodium chloride. Because they're all bound up in this relationship of 1 to 1 produces 1, and the mass of the sodium plus the mass of the chlorine equals the mass of the sodium chloride. So if I know how much I want to make, I know how much I need. If I know how much I'm given, I know how much I can produce. Using a reaction equation and the relationships between moles and counts and using the atomic masses in terms of grams per mole. Let me see. Now this mole concept here that we've just gone through. Review questions 8 and 9. We're getting to the place right now, we're almost done with the content for the chapter. Okay? I'm not exactly sure what's going to happen next week in here. There will be a sub while I'm at my doctoral seminars. So whether that's going to be movies or I might videotape myself going through the practice problems and the extra practice problems so you can actually go over them in class, or I might not have to record them again this year because last year's class for this module is online, so you could have already listened to the last year's version of this same lecture series for this module. It's there, so if you miss something, I tend to post several for this week's lessons after this class. I tend to finish editing them and post them to YouTube. But you have last year's you could go back and review as well. Because we are just maybe 2 pages from the end of the chapter. So I would give you that this was review questions 8 and 9, practice problems 6, 7, 8, and 9, extra practice problems 7, 8, 9, 10, 11. But frankly, that's virtually the end of the chapter anyway. So we kind of cleaned up all but a couple right here. Now, the very last section that we need yet to go over is that using the mole concept in chemical equations that starts at the bottom of 265. And frankly, I've been referring to its use all along. This is kind of an add-on thing here, but maybe just as another example. You notice on 265, they give you an equation for something. Now, does everybody see the reaction equation there? What kind of a reaction is that? Pardon? I'm looking at 265, like three lines from the bottom of the page. They have a formula there. Look at the form. I've got a fuel and oxygen. Combustion. What kind of combustion? Complete combustion. I know it's complete combustion because carbon dioxide as a product. Good. So let me write the formula that they have in the book there. CH4, methane. I'm not going to use the phase symbols, but this is a gas, and it reacts with 2 oxygen molecules to produce a carbon dioxide molecule and 2 water molecules. Like I said, I've been alluding to this all along, and I've said it many times, but what I see up here with the different coefficients is that the coefficients in the front give you the proportions. Remember I said all along, 1 of these and 2 of these produces 1 of these and 2 of these. Same way that 10 of these and 20 of these produce 10 of these and 20 of these. You look at the coefficients in the front, and they're proportional to each other. Now we add the mole idea. 1 mole of methane and 2 moles of oxygen produce 1 mole of carbon dioxide and 2 moles of water. That's all this last section is talking about. Now, what it's not saying, because we've been relating moles and grams, remember the moles to grams ratio, that is based upon the individual element. It's not based upon some standard for everybody. 1 mole being 6.02 times 10 to the 23rd of them, that applies to everything. That's why I use the example of a zebra. Having a mole of zebras, well, that would be around the Earth, like more than a mile. Because a zebra, if you didn't know it, is bigger than a ping pong ball. Okay? So, this would be a huge amount of zebra meat that needs to be dealt with very quickly, right? So, a mole of anything is the same count of anything, which is why it's universal. The mass of something is unique to that thing. Potassium has a different mass than calcium, has a different mass than cesium, okay? Which is why you cannot say, and this is one of the fundamental errors which you cannot say, that 1 gram of methane and 2 grams of oxygen gas produce 1 gram of carbon dioxide and 2 grams of water. You might look at it and go, well, there's 1 and 2 that makes 3, 1 and 2 that makes 3, conservation of mass. No, that's not what's happening. You cannot say that. The coefficients do not relate masses. They relate counts. I need one, for every one of these, I need 2 of these. And for every 1 of these and 2 of these, I can produce 1 of these and 2 of these. That's what the coefficients are telling you. It's not the mass. It says in chemical equations, the coefficients which appear to the left of each substance tell you how many moles of that substance must be used in the chemical equation. Because we're not going to ever really work in the lab with 1 molecule and 2 molecules produce 1 molecule and 2 molecules. We're going to use stuff we can actually measure and work with. So we're going to react 1 mole of methane with 2 moles of oxygen to produce 1 mole of carbon dioxide and 2 moles of water vapor. If I said I'm going to react 4 moles of methane according to that reaction, 4 moles, how many moles of oxygen would I need? Well, if 1 needs 2, then 4 needs 8. And 3 needs 6. And 10 needs 20. See, they're related 1 to 2. But I also know that if I react 1 mole here of methane and I have sufficient oxygen, how much carbon dioxide am I going to make? If I react 1 mole of methane, if I combust it, how much carbon dioxide is going to be produced? 1 mole. 1 mole and 2 moles react to produce 1 mole of carbon dioxide and 2 moles of water. And now I know that I can tell you how many molecules of water are going to be made when I react 6.02 times 10 to the 23rd molecules of methane. It's going to make 12.04 times 10 to the 23rd molecules of water. Why? Because for every 1 molecule I combust, I create 2 molecules of that. Why? Because I have a balanced reaction formula. It has to be a balanced reaction formula. That's why we practiced balancing last module. That's why we got to the balanced reaction equation, so that we could then say, hey, in this whole equation here, if I know that that's the equation that we're talking about, and you tell me that I produce a certain number of molecules, or I combust a certain number of molecules of oxygen, I can tell you how much methane I needed to do that, and I can tell you how much carbon dioxide and water I created by doing that. If you tell me I do this reaction and I obtain a certain number of molecules of a certain number of moles of water at the end, I can tell you how much carbon dioxide was also produced, 1/2 as many moles. And I can tell you that in order to get that, I had to react the same number of moles of oxygen as water, because it's a 2 to 2 relationship. And I took 1/2 as many moles of methane to do it, because it's a 1 to 2 relationship. The coefficients in front tell you how many moles of that thing you need to have a perfectly balanced reaction equation to be fulfilled for it to actually occur.